Welcome back. We've talked about a lot of systems in the last few weeks. I'd like to spend just a little bit of time talking about how we actually do some of these computations. So here's a quick summary of various least squares problems and solutions that we have discussed. First, if we have a full column rank, then A, and so I guess context up here, although we're getting quite familiar with this, y is equal to A x, and there may be an error in there, but what matters is that we have A and that we have our observation y. Okay, so if we're looking for a pseudo-inverse, when A has full column rank, we're computing A transpose A inverse A transpose y. We can use a pseudo-inverse solution also if A has full row rank. And that will give us x hat is equal to A transpose A transpose inverse times y. We also looked at the situation where we maybe didn't have full rank, or maybe we have full rank but we have a wide range of singular values in A, which would lead to error growth. So Tikhonov regularization gave us a solution that looked like essentially what we had for our pseudo-inverse, except now we apply a diagonal offset to ensure invertibility, and also to reduce the range of singular values, and therefore the growth of the error in the due to the inverse there. Okay, so something we did not talk about, but we'll put it in here as kind of a bonus for all the tuition you pay. It's just our way of saying thank you. And this is the generalized Tikhonov regularization, and it looks like this. D transpose D inverse A transpose Y. So the only difference here is now instead of the identity matrix, we have some symmetric positive definite matrix indicated by D transpose D. We also discussed our weighted least squares. In this case, x hat is equal to A transpose W transpose W A all inverted times A transpose W transpose W Y. And finally, the best linear unbiased estimator, blue, x hat A transpose R inverse A inverse A transpose R inverse Y where R is equal to the expected value of the error times the error transposed, and the error expected value of the error is 0. So in that case, we would add in this error term up above. It's implied to be there, but in blue we have to explicitly take that into account. So each of these solves a symmetric positive definite set of equations. And there are good ways and bad ways to do these. So let's say each solves a symmetric positive definite set of equations. And in general, there are better ways to do this than direct computation. For example, if we have a triangular system, something like this, A11, 0, A21, A22, so on up to AN1 to ANN. Let me just make the whole for part 0. Now this is not symmetric, but to solve for x, is pretty easy. X1 is equal to Y1 divided by A11. And X2 is equal to 1 over A22 times Y2 minus A21 X1, and so on and so forth. And we know each of these terms. So this is solvable. With order n squared operations instead of x equals A inverse y, which is order n cubed. Okay, so that's a pretty big savings. Turns out that it's very rare that we can get anything that's less than order n squared, but we can often get order n squared. Now if you have something small, if it's a 3 by 3, you're saving on the order of 3x operations. But if it's 100 by 100, boy, 100 times faster is something that's really compelling. So this particular example, this triangular system, order n squared, doesn't fit this symmetric positive definite set that we've talked about. However, different decompositions that we can perform get us into a state when then we can use this particular form. And so let's talk about a few of the kind of the range of complexities involved. So if we exploit the structure of our matrix A, or some aspect of A, such as A transpose A plus I, quantity inverse, and so on and so forth. If we exploit the structure there, then there's often a lot of savings that can be had. So we're finding that y is ax, and we're solving for x. If A is diagonal, then we have something order n. We have n rows. Each row can just be solved by dividing the diagonal element into y, and we're done. So this is by far the most efficient and also the least interesting of these problems. If A is triangular, and then we saw this already, we get order n squared. If A is orthogonal, then we have order n squared, because the solution is found as x hat is just equal to A transpose y, and the matrix multiplication is order n squared. So if A is tuplets, then we have order n squared again. And we've run across this once before, but just as a reminder, this type of a matrix looks like so. 1, 2, 3, 1, 2, whoops. Mine's a better 1, 2, 1, and then over here we have something else. Say 10, 11, 10, 12, 11, 10, and so on and so forth. So each row is a shifted version of the row above it, but as we shift to the right, new samples come in on the left. So that would be a tuplets matrix. We'll spend a little bit more time with that in a bit, but this shows up, I guess I should mention, for correlation matrices are of this form, and so it's a very common form. The R matrix that we had for our blue solution would be of this form, for example. So if A is circulant, then we have order n log n, which is better than n squared and much better than n cubed. So a circulant matrix, basically we can use Fourier techniques with that. And I guess for completeness we should mention for the tuplets matrix you use the Durbin algorithm. And finally, if A is general, then the complexity is order n cubed. Multiple ways to get to order n squared. Order n log n is the best, but in general we have order n cubed. So let's talk about some of the ways that we get there. First, we can perform a Cholesky decomposition on symmetric positive definite matrices A, as A is equal to L transpose. So L is a lower triangular matrix. And once we've done this, then we use the triangular solution method that we talked about on the previous page. Twice to find the solution to AX equals Y. And so although it's obviously now it's order 2n squared, that's not the way the complexity notation works. It's still we just say it's order n squared. In other words, the complexity increases with the square of n. There may be other factors in there as well, but we're still in the same order. So order n squared. The problem is we have to first find the Cholesky decomposition. But we get the same for the QR decomposition. So the QR decomposition can be found using the Gram-Schmidt approach. And that gives us A is equal to Q R. This is an orthonormal matrix. I also referred that to that as an orthogonal matrix up above. And this is upper triangular. So, how do we find this using the QR decomposition? Well, essentially what we're saying is A can be transformed into a, if A has full rank, we can transform A into a set of orthonormal basis vectors. Well, how do we do that? We do that by the operations by row operations. And so essentially we're saying that our orthonormal basis is equal to A R inverse. These represent operations of the Gram-Schmidt process. So we can keep track of these operations, and as we build it up, we can either build it up and find R or R inverse. And in this case, we're most interested in R inverse. This is often used in communications. Now, once we've done this, we solve this in two steps. One step involves multiplication by Q transpose. Then the next step involves solving using the triangular method. And so we also get order and squared operations here. You may have observed the problem with these two methods, and that is finding the Cholesky decomposition or the QR decomposition has increased complexity. So this is most useful when, let's do this. These methods are often used if the ax equals y equation needs to be solved for multiple y's. So once we've found this decomposition of A, we can apply this to any number of observations that we have. We use it over and over and get order of n squared, and we only pay the decomposition price once. However, they're often used even for a single y or a single set of observations, because they're more numerically stable. Then solving for A inverse and then multiplying.